Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. So as we said in the previous lecture, we have almost come to the end of our discussions pertaining to root locus. Eventually we did see at least one tool for designing controllers. So as we said right at the beginning of this course that there are two parts to this course. One is of course, or rather for that matter for any controls course there are always two parts. One part has got to do with analysis, the other part is about synthesis. So at least we have seen one method of synthesizing a controller in order to meet certain performance specifications as well as both in steady state as well as in the transient response, right. So steady state as in the steady state error, transient implies things like rise time, settling time, percentage overshoot, etc., etc., right. So before we bring this to a complete closure, perhaps there's something that I should just illustrate, right, and this will not really take too much effort to see because we've already discussed about op amps, operational amplifiers, and seen what the transfer functions of op amps in the inverting and the non-inverting modes look like. Of course for the idealized op amp, we've also taken a case in point about the non-ideal op amp and its equivalent circuit, but we'll not get into that. For now we'll just be satisfied with seeing certain realizations of these controllers. So first we saw the PD, the PI and the PID, which were controllers and which we claimed cannot be realized unless you use these active components called op amps, right. And then we saw some approximations of these PD, PI, PID in the form of lag compensators, lead compensators and lag lead compensators, not necessarily in that order, but I just want to point out that these compensators, the lag, the lead and the lag lead, they can be realized whether you want to use passive elements even then, and even if you want to realize them by active elements, even then you can realize these, right. So they are more versatile in that sense, right. And also later on we shall see that controllers like the PID controller actually in their pristine form as we presented them do not have something called a state space realization because they are improper, right. So that is also another consideration. In fact, in this whole area called robust control, when we seek controllers that are stabilizing, we don't admit controllers of the form of PID, okay. We only admit strictly proper or at most biproper in some cases as the structure of a controller, right. So let's get into that. We've said much about the realizability using active and passive, so here goes. So as we know that if you have an op amp in its inverting mode, then of course the non-inverting mode is earthed and you have this at the input side is the impedance that you call Z1 and at the output side you have the impedance called Z2, right. And please recall that the op amp has infinite input impedance, zero output impedance. This is almost like a virtual short and this is therefore almost like a virtual ground. So this is the V out, this is the V in, okay. And we know that in this inverting mode the VOS upon V in S, this transfer function is given by minus Z2 upon Z1, right. It's quite simple to derive really. You just have this at this junction you just apply KCL, so therefore you have V out minus 0 because this is virtual short, so it's earthed almost. So V out minus 0 over Z2 plus V in minus 0 over Z1, right. So therefore V out over V in, yeah, is minus Z2 over Z1. Now hereafter we will assume that this is the structure of the op amp, this is the structure of our controller, and we will give you sort of the structures of Z1 and Z2 that will eventually lead to the different kinds of controllers. So first of all, start with the static gain K, because that was the basic form of the structure of the controller that we saw at first, the root locus with only the gain parameter. So let me just have two columns for Z1 and Z2 like so, right. So this is, let's say, R1 and this is R2, okay. So this is basically what? This is the controller type. So this is a proportional controller, right. Now suppose you want a PD controller, or rather let's look at some bit by bit, elements bit by bit, okay. So let's say you have a C and you have an R over here. So this is basically a D controller, just a derivative action, you can just check, right. And I think we have already done this earlier at some point. So C will be replaced by 1 upon Cs, right. So that is going to be your Z1. So the Cs goes up then in the numerator and it differentiates, right. Okay. So then about the integrator, you just reverse the roles of these two. You have an R here and a C here, and that gives you an integrator. So now if you want to consider a PD controller, for instance, then what you do is you put this resistance in parallel with the C, yeah, you call this R1, you call this C. This is the structure of Z1, and the structure of Z2 is just an R. So this is going to be your PD controller, right. And then of course if you want your PI controller, you have your R as it is here, let's call this R2, yeah, you have your R as it is on this side, let's call this R1, and on the other side you have R2 in series with a capacitor, right. So this is going to be a PI controller, right. So now if you want a PID to be cooked up out of this, it's almost straight away you can see that you will just have to put in the PD block from here and the PI block from here. So then what you have is this is R1 and this is a C1, right, and then on this side you have R2 and a C2, right. So this is a PID controller. So these are all active realizations of different controllers, right. Okay. So now as we said that we don't want to always use these active elements, we also want to be able to design compensators using passive elements, right. So what if we want to do away with this op amp, because naturally this op amp has external voltage sources, right, yeah. So we don't want this active element in place. Suppose we want to build our circuits or build our controllers using only resistances and capacitances, can we do that? So then it turns out that you still have structure such as this in a circuit, in an electrical circuit, Z1, sorry, not this, yeah, then you have Z1 here and a Z2 here, right. So you say that you apply your Vi here, or rather V in here, and this is going to be your V out, the output voltage over here, right. So this is the, just like we said that this is the prototype for the active circuit, this is the prototype for the passive circuit. And now again we are going to do the same thing, we are just going to show you the structure of this Z1 and Z2, and from there you can immediately see the connection and the similarities between the two, right. And then we will say what type of compensator it is. So I will leave it to you as an exercise, please take this as an exercise to actually evaluate these transfer functions and relate these resistances and capacitances, these parameters of this electrical circuit with those gains, or rather even better with the controller poles and zeros, right. So you know that a PD controller has a 0, PI controller has a 0 and a pole at the origin, of course. So if you put them together, if you cascade them together, right, in this form as it is, then how are the poles and zeros of those two compensators, right, the two zeros and of course the one pole is always at the origin. So how are the two zeros related to these parameters, okay. Take that as an exercise to evaluate. That you should now be able to do, since we've already discussed what an op amp is like. So let's say now you have this a resistance here and a resistance and a capacitance here. This is R1, this is R2, this is C, yeah. So this is basically a lag compensator, right. So this is a lag compensator. Then let's say you have an R1 here and a C here on the Z1 structure, and you'll immediately see the similarities. Just like we said, the lag comes from the PI as an approximation of the PI, and the lead comes as an approximation of the PD, right. So this kind of follows straight away, okay. So this is a lead compensators realization. And now if you want to put both of them together, then exactly as before, as we did for the PID, here you will have R1, C1, and then here you will have R2, C2. So this is a lag lead compensator which we designed in the previous class, right. So again, you can take this as an exercise to check that if this is how you are going to realize, yeah, if this is how you are going to realize your passive lag lead compensator, there is one limitation, okay. So this structure has a certain issue, and the issue is that, notice when I said that there was a lag compensator looks something like this, where of course Z is greater than P is greater than 0, right. So this is a lag. A lead compensator on the other hand had S plus Z2 upon S plus P2, yeah, where the order changed. So you had P2 greater than Z2 greater than 0. So this should I'll change this is Z1, this is P1, right. Now it turns out that you can see that this Z1 over P1 ratio in the lag compensator is greater than unity, right. Suppose you call that ratio alpha, alright, then you will notice that by virtue of this particular form of structure of this lag lead compensator, the issue is that whatever is the ratio in this particular form, if you put it in this structure, yeah, and you do a little bit of algebraic manipulations, you will see that whatever turns out to be the ratio of Z1 upon P1, yeah, is the same as the ratio of P2 upon Z2. In other words, you cannot design the lag compensator and the lead compensator independent of one another. If you recall in our previous lecture when we designed those compensators, this was very essential. Remember, when we designed the lead compensator part, which was an approximation of the PD controller, the angle contribution was crucial in order to meet the angle criteria, yeah. So I just arbitrarily chose this this location of the 0 of the lead compensator to be to the right of the location of the putative PD controller, right, and then accordingly the location of the pole got fixed up automatically, right. This ratio of this pole and 0 of course depends on this arbitrary choice that I made, notice that, okay. Now secondly, when designing the lag compensator, yeah, when designing the lag compensator you would have, if you recall, when we were designing the lag compensator in order to ensure that the steady state error came down to a very low value, the point of concern was we wanted to get a ratio, yeah, of that Z1 over P1 to be sufficiently large so that the Kp value, Kp by I mean the position error constant, Kp, as in the steady state error analysis we've studied. So we wanted that ratio to be matched in such a way that the Kp was suitable so that the steady state error given by 1 upon 1 plus Kp was good enough for us. Now clearly, if you are now saying that this ratio must remain the same for the lag compensator and the lead compensator, then I am basically restricting the location of this 0 of the lead compensator, which was earlier freely chosen by me. Remember, I chose it very freely, I just assigned it I think minus 4.5. If you go back to the previous lecture, you will see. So this minus 4.5 is just a trial and error sort of a choice that I made. And this is very important because we've seen earlier that once you design a lag lead compensator, the job isn't over. You have to simulate. And if the simulation doesn't work, you have to go back to the drawing board and redesign. So it always helps if you have multiple choices for this 0 of the lead compensator. But now, notice that there is this coupling between these two relations. I mean, once you have fixed up the ratio of the pole to the 0 of the lag compensator, right, to get a low steady state error, the ratio of the lead compensator 0 to the pole also gets fixed up as its reciprocal accordingly. So that is a problem with this structure, okay. So in order to bypass this, unfortunately what happens is use is made then of an isolating unit. So op amps are very good at isolating because they have infinite input impedance, they prevent loading of the circuit. So basically if you put a unity gain op amp like this, it might seem like this serves no purpose, right? What's the use after all? Anyway the voltage gets loaded. But remember, so here's the utility of this sort of an op amp, okay. So then I'm going to now draw this structure so you can see what this is. So this is R1, this is C1, okay, this is the input side, and this is R2 and C2, okay. So this is the output side. Now notice the only change between this circuit and this circuit is I put an op amp somewhere here, yeah. Now you might wonder what is this op amp doing after all, right? Because after all this is just adding a unity gain, but what this op amp is doing in addition is, remember here this circuit gets loaded, the Z1 and Z2 are coupled, okay. So whatever current flows through this also flows through this, right. On the other hand here, because of the infinite input impedance provided by this op amp, whatever voltage appears across this gets just reflected here and no current flows, okay, across through this op amp. So basically this op amp is now used, op amp just prevents loading. So whenever you see an op amp in this unity gain configuration like this, you would guess that the utility of that op amp is essentially to prevent loading from one part of the circuit to the other part. In other words, it helps in isolating, yeah, and because it helps in isolating, now you can sort of treat this PI/PD, this lag and this lead part as if they are cascaded together, and now they can be chosen independent of one another, okay. Now the lag part, the 0 and the pole of the lag part can be solely determined by this R1 and C1, and the 0 and the pole of the lead part, yeah, that can be solely determined by R2 and C2, okay. So that basically gives us this required decoupling. So unfortunately, even though we tried to avoid the use of op amps to realize the compensator, it turns out that there is this limitation of this realization using passive elements only. So sometimes you cannot help but use this active element, okay. So you might wonder, if we are ultimately using active elements, can we not realize all of these fellows using just active elements as it were, and it turns out that you can, okay. So I leave it that as an exercise for you to check that now if you want to basically use an op amp like this, yeah, Z1 and this is Z2 like so. So take this as an exercise to figure out what should the structures of Z1, Z2 be like for a lead compensator and a lag compensator. So, a hint is that they will both look the same, okay. So, you figure that out, okay, which configuration of, whether it is the parallel combination of the RC or the series combination of RC, whichever one works, just try to figure that out, okay, which one is easier to work around with, try and figure that out, okay. What I am just telling you is that the configuration is going to be the same for the lag and the lead compensator, and that makes perfect sense, because after all the lag and the lead compensator vary in only as much as the ratio, yeah, the form of the transfer function is the same. So, it then makes sense that whatever works for a lead compensator should also work for a lag compensator structurally. The only thing that you have to tweak around is the values of these resistances and capacitances at the input and the output side, okay. Now, of course, as an addendum, you can immediately guess that if you want to now put a lead and a lag compensator, then you put two of these blocks in cascade. So, you put another Z1 dashed like this, yeah, and this is Z2 dashed like this, yeah, and you join this connection. So, if you join this connection, then you will see that if this is your Vi and this is your Vo, if one part is the lag part, the other part is the lead part, does not really matter which is ahead of which, right. So, then this combination of these two cascaded together like this, when you connect them across like this, yeah, this gives you a lag lead compensator. So, the only exercise for you to figure out is what should be the structure of Z1 and Z2 in order to give a transfer function like this, whose poles and zeros can be determined then by the parameters of these circuit elements, okay. So, with that we kind of bring to a culmination our discussions on root locus based compensator design, and now we have seen also this realizations of these compensators using electronic components, right, and that should suffice. Of course, that is not to say that this is everything there is to a root locus. There are several other things you can study when, for example, the closed loop poles vary with respect to multiple parameters, then you have something called root contours. The principles would still be similar, but if you are interested, you can also study about root contours, okay. Those are another interesting topic. The other interesting topic would be, as far as the compensator design is concerned, is when instead of having a configuration like this that we have studied here, so this is your controller, this is your plant, and this is, you know, instead of this configuration, what if you have a G here and a controller in the feedback path, okay. So, even such controllers can be designed using the principles of root locus that we have learned. Things will change around a little bit, but it is not really too much of a stretch. So, I invite you to study these alternate structures of the controllers, and finally, you can combine these two types of controllers and call it a sort of a 2 degree of freedom controller. You can have some pre-filters ahead of this summer here, on the left of this summer here. You can do lots and lots of things, okay. So, those are of course topics that are slightly more advanced, but within the purview of this course, if you get into that, then we will not get out of this topic, and you know, just we can dwell on root locus for the remaining part of the semester, and that will be it, right. But since there are a lot of other exciting topics to cover, so we will, for our purpose, bring the discussions on root locus to a closure now.
Sorry about this, there has been a slight error in this circuit diagram, but nonetheless the idea is to leave it to you as an exercise. Yeah, so here's how the circuit would look. You can actually check and verify that this indeed is a realization of the required compensator, right. This is C1, and let's call this what, R3, yeah, and you'll also have another resistor here, which probably we haven't used. What symbol? R4, okay, so let's use R4, right. So this would be the actual realization, and this op amp would provide for some isolation, yeah.
And the next topic that we are going to now discuss is Bode plots, yeah. So frequency response. So now we are going to take a paradigm shift. So far, all our performance metrics and performance parameters have been determined in terms of those time domain responses, right. Now we are going to study the behavior of the system in the frequency domain. And why is this of importance to us? So here is the setup for this study. Suppose you have a transfer function g of s, yeah, and earlier remember we were just studying the step input and the response to the step input. Now say we give an input of the form a sin omega t plus b cos omega t, or rather the other way around, whatever, a cos omega t, because we will see that shortly why I am preferring this, a cos omega t plus b sin omega t, yeah. So of course the Laplace transform, because I want the s to appear with a, that is why I put it like this. So it is as plus b upon s squared plus omega squared. That is basically the input that is being applied. And here you have, so this is RT, in other words RS is going to be this, okay. Now why are we interested in studying this form of response? Notice what this essentially means is that we are applying a sinusoid of a certain frequency and a cosinusoid of the same frequency, right. And while we are doing this, of course, then this can be merged together to give us a sinusoid of the same frequency with only a phase shift, right. So that is what we are giving as an input. So why does this interest us? Why are we interested in this sort of a input, and why are we interested in studying the response of the system? We saw earlier when we were studying the step response, it made some sense, right, because you are giving a constant input and you want to see how the system responds to a constant input, and we can relate to constant input. They appear in at several junctures in our life, right, when we apply a constant voltage, or when we have a constant current source, when we apply a constant force, when we apply a constant torque, these can be visualized. But where do these sinusoidal kind of signals originate from? Well, one source is of course alternating currents and voltages, right, which is a very important part of our studies in electrical engineering, right. The other thing is, now notice that if you have not necessarily a periodic signal, but if you have a signal that is like this, right, this signal, if you have studied Fourier series and Fourier transforms, you would know, of course Fourier series is only applicable for periodic signals, but even if you study Fourier transforms, you would know that this signal can be thought of as an aggregation of signals of different frequencies, yeah. So now this can have some very high frequency components like this, yeah, and this can also have some very low frequency components like this. Now overall, whether the signal, whether this signal contains more of high frequency or more of low frequency will be determined by the relative amplitudes, yeah. So we can cook up this signal, yeah, as a combination of several such different kinds of signals of all possible frequencies from 0 to infinity, yeah. That is basically what this allows us to do, right. Now once we are able to do that for any arbitrary signal, it will then be of our interest, because remember, beyond a certain high frequency it is hardly perceptible to us, right, because if it is oscillating very quickly, we will have these low pass filters, yeah, which will reject frequencies beyond a certain cutoff. Most control systems, most practical systems are of low pass in nature. Of course all of this low pass and all will begin to make more sense as we go deeper and deeper into Bode plots, right. By low pass we mean that they allow low frequency signals to pass through them undistorted, unadulterated almost, yeah, possibly with a high gain in fact. Again, these gain and all these terms will make sense as we go again into Bode plots. So it's like an egg and chicken problem, but for now you just go on with me, stretch your imagination a bit and try to be on the same page with me, and we will see by and by how these terms make sense, right. So the point is that now we want to understand that a signal like this, which could potentially be an input to a system, yeah, so we want to find out how this system, this linear time invariant system, so remember the moment it is represented as a transfer function, it is basically a linear time invariant system. Yeah. So what can we say about this linear time invariant system? We want to find out what the response to this sort of an input will be. Now because it is a linear system, therefore the response due to a sum of signals is equal to the sum of the responses due to those individual signals. This is the basic property of linearity. So now it makes sense then that if we can split this signal up into these different components, and if we can tell how this particular system amplifies or attenuates each and every signal of different frequency, right, then we might have some idea, right. Then we add up the responses after passing each of these individual components through this block, whatever comes out, whatever this block spits out, I will have some idea about what this response to this arbitrary signal will be like. So therefore this frequency domain response, it's frequency response, right. So in every frequency, in every possible frequency that we might be interested in, how does this particular LTI system act on signals of different frequency? Yeah. So there are two things that an LTI system generally does to such signals. One, it amplifies or attenuates the amplitude of the signal. Two, it gives a phase shift. But if it's an LTI system, remember an LTI system, so for an LTI system, the frequency of the input and that of the output must be identical. Okay. So you can immediately check this here. If you take this, so let me go to the next slide. So if you now want to find out this y of s, you will see that you want to apply this multiplication g of s times r of s. Right now if you expand this in partial fractions, what can this partial fraction contain? This partial fraction will contain those modes that are inherent due to the poles of gs and those modes that are being introduced by the input, that is some terms like k1 upon s plus j omega plus k1 star as we have seen earlier by s plus minus j omega, plus these are modes due to g, right. So naturally, yeah, if you give a particular input to this signal to the system of a particular frequency, your output, yeah, your output cannot contain signals of other frequencies. Of course you might argue that, hey, look, there are these modes due to this other poles of g, right. So they might be signals of different frequency, but remember, here's one crucial assumption we make. We say that this g of s is a stable transfer function. All right. So what does that mean if to say that g of s is a stable transfer function? What it means is, excuse me, what it means is that none of the poles of g are on the closed right half plane, all of them are in the open left half plane. So there isn't even an imaginary pole, okay. What that implies is that these modes due to g, so this implies that these modes due to g decay with time. So now if I am concerned with steady state response only, yeah, I should only bother with k1 and k1 star. So the moment I know k1, I know k1 star as well. Yeah, makes sense, right? Okay. So now that we've done that, now that we've established that, so basically what this Bode plot or this so called frequency response is concerned with is this steady state response. That is the fundamental thing to be remembered. So therefore it does not make sense, you can always draw Bode plots for any arbitrary transfer function, but it will not make much sense, because remember, to start off with, this is a very crucial point, remember, to start off with we are saying that this entire frequency domain study is predicated on the assumption that there is some steady state. When can there be a steady state? There can only be a steady state if the system is stable in the first place. But if the system isn't even stable, it doesn't make sense to talk about a steady state. What if some of these modes are unstable? They'll blow up. So there is no steady state. The question of a steady state doesn't arise. So therefore, this is a very important assumption that whenever we are drawing, of course you can draw Bode plots for any arbitrary transfer function, whether it's stable or not. But again, recall that it's not going to make much sense unless it actually corresponds to a stable transfer function. Yeah, later on we will revisit this topic and talk more about this, but for now we will do well to remember that this is what we are dealing with. So now what is this K1? Of course this K1 is a residue, so I can just excuse me, so I can just as plus b upon s squared plus omega squared times g of s. Yeah, I just multiply this by s plus j omega and let limit s tend to minus j omega. Yeah, that's going to give me my K1, right? So let me quickly write that down. That's going to be equal to a j omega plus b, okay, let me say this is b omega, right? I think I missed a trick here. It's going to be b omega, no? Because it's sine, so this omega must come here. Yeah, that's what was looking a little off to me. So this is going to be omega, aj omega plus b omega, and this is going to be, so minus 2j omega. You can check this s plus j omega cancels out this s plus j omega from the denominator, and you're left with only s minus j omega. So when you substitute s is equal to minus j omega, you get minus 2j omega times, so this omega will obviously cancel out because this omega is non-zero, so you can cancel it above and below, times g of j omega, right? So let me write that down. So therefore what we have here is, let me see, okay, there's a minus sign here, of course, and a minus sign here, right? So what we have then is, let me go back, that's a upon, so this, you see this omega is not equal to 0, right? So therefore this omega I can safely cancel out from here. Yeah, this omega and this omega and this omega, all of this gets cancelled. Yeah, so then what I'm left with is, of course, this j also gets cancelled for the first term, so I'm just left with a by 2. Yeah, that's right. So for K1 I just have a by 2. What about the imaginary part? You see I have this minus j in the denominator, so I can multiply above and below in the numerator and denominator of the second term by j. So I'll get a minus j times j, which is just 1. Yeah, because j is the square root of minus 1, remember? So j squared is minus 1, and this existing minus sign already makes it plus 1. So it's essentially jb by 2, right? So we have plus jb by 2, and multiplied with that we have g of minus j omega. That's it. And notice that we already know that the second term, this coefficient, this residue is nothing but the complex conjugate. Remember, we had already discussed this when we were discussing the inverse Laplace transform for second order terms such as these, right? So of course I know then K1 conjugate is going to be nothing but a by 2 minus jb by 2 times g of j omega. Remember that if you have two complex numbers z1 and z2, and if I take their conjugate, that is the same as taking the conjugate of the individual complex numbers. So here also I have two complex numbers, one is of course a plus jb by 2, the other is g of minus j omega, right? So if I take the complex conjugate of overall K1, then it will be of course the complex conjugate of the first term, which is this, and the complex conjugate of the second term. So I conjugation, I get this, from this with conjugation I get this, right? Okay, Now having seen this, we are now in a position to sort of okay, let me write this here. So this is y of let us say, so yeah, so this is y of s. Of course I know that this, I am going to ignore all of these other modes as I have shown that they decay with time. So from hereafter I am not going to or rather let me use y tilde, which is nothing but the steady state response, okay, rather the non decaying part of y, yeah. So that is basically it. So I am going to, that's just a way of saying that I am going to ignore these other modes due to G which decay with time, simply because G is assumed to be stable. If it is not stable, it does not make sense to talk about a steady state behavior, which is what frequency response is supposed to do. Alright, so now having seen that, what can I write this as? Therefore, y tilde is going to be this a by 2 plus j b by 2 times g of minus j omega. Remember, this is all a constant because this omega is a fixed number, right, by s plus j omega, I believe. Yep, it is s plus j omega plus a by 2 minus jb by 2 times g of j omega upon s minus j omega. At this juncture I am going to talk about something which will turn our attention to this term and naturally also to this term. Now remember that this is now nothing but a complex number, and as with every complex number we can split this up, right, into a magnitude and a phase, right. So what is going to be the phase of this complex number? We know that again, you know, that z1, or rather if z is a complex number, so let us say z1, z2, z, these are all complex numbers, then we know that the magnitude squared of z is nothing but z times z conjugate is equal to z conjugate times z, right. That is what we know about this. So therefore obviously this is also nothing but g of j omega and g of j omega taken with its conjugate, but we know that its conjugate is nothing but g of j omega times g of minus j omega, yeah. So if you just reverse the sign of the imaginary part of a complex number, you get its conjugate, and that is the same principle we are using here, right, that is the same principle we use to get the conjugation here, so it should be obvious by now, right. So immediately notice that this is nothing but what we call as the so called gain of the system, right. We are interested in what the gain of the system is, okay. So let us then define this m omega squared, yeah. So we define this in this fashion, where m omega is the gain of the system at j omega, or rather at a frequency of omega. So for a sinusoid of frequency omega, what is the amplification? Yeah, we will later see that this in more concrete terms, why we call it so, but at this point you might notice one thing about m omega, that m omega is equal to m of minus omega, which means that it is even, yeah, straightforward to see here. You see, you replace omega with minus omega, so you get g of minus omega and g of minus j omega and g of j omega, right. So it is an even function, yeah, it is an even function. So we notice that. What about the phase? Yeah, what about the phase of this complex number? So let us say we have phi of g j omega, that is going to be nothing but the tan inverse of the imaginary part of g j omega divided by the real part of g j omega. Now note, yeah, there is nothing so special about this other than the fact that this phi of g j omega is going to be minus of phi of g of minus j omega, yeah. So in other words, it is an odd function. Is it very obvious to see? Well, of course, just turn your attention to this expression here. Yeah, if you just replace j omega with minus j omega, yeah, you see that this real part doesn't change, right, but the sign of the imaginary part changes. So of course, if you take the tan inverse of x and the tan inverse of minus x, yeah, you know that tan inverse x is equal to minus of tan inverse minus x, and for the same reason we can conclude that this phi, in fact later on we shall omit this g, it is understood that this is the phi of g. So when it is obvious from the context, we will just say this is phi of omega is equal to minus of phi of minus omega. When it is understood from the context that basically phi represents the phase of the system at omega, alright. So we make these two observations and these will help us. How will this help us? Eventually now we are going to write this g of j omega as we do in for any complex number in its polar form. We are going to write this as this, yeah. So this is going to be the magnitude, this is going to be the phase, right, where this is of course the argument of g. So this is a standard representation of a complex number that we are all kind of familiar with at this point, yeah. So having seen this, you might wonder why I am taking this digression. The reason being that notice we are now going to again cast our attention back to this y tilde, which is the steady state part of y, and we are going to take the Laplace inverse of y tilde, yeah, and that is going to lead to okay, so it is a by 2 plus jb by 2, and now I am going to replace this g of j omega with this, yeah, I am going to substitute this here. So what I can then write is, excuse me, what I am going to then write is this m omega times e to the j phi omega, right, times, notice now I am taking the Laplace inverse of the individual terms. So what is the Laplace inverse of this? This is e to the j minus j omega t, isn't it, right. So this is e to the minus j omega t, yeah, or so I believe it is indeed, yeah. Oh, this is the minus sign, I am sorry about that, so I should actually replace this with a minus sign here, yeah, because remember this first term here had g of minus j omega. So g of minus j omega is of course the m omega remains the same, but the phi gets inverted in the sign, yeah, good I noticed it early, right. Then what about the second part? We have a by 2 minus jb by 2 m omega, all the same. Now this will have, notice, g of j omega, so it is just going to be e to the j phi of omega, yeah, times e to the, of course because of this part is going to be e to the j omega t, e to the j omega t. And now I am going to simplify it in a certain way. So let me first take as many things as I can take common outside. So of course the first common thing is m of omega, which is of course what I have called the gain due to the system at a frequency of omega, and then let me take the terms that are pertaining to this a by 2, yeah. So let me take this term related to a by 2, and what I have then is e to the j omega t plus phi plus e to the minus of j omega t plus phi. So note that I am omitting this phi omega, yeah, it is understood that it is a function of omega, right. And then I have of course plus j by 2, jb by 2 in fact, and then I have e to the minus j omega t plus phi, yeah, because this minus and minus, I am taking the minus out common just like I did here, with a minus then e to the j omega t plus phi. Yeah. Now recall, again recall that cos theta is equal to e to the j theta plus e to the minus j theta upon 2. So this is again recall, and sin theta is equal to e to the j theta minus e to the minus j theta upon 2j, or j times 2, it is all the same. Yeah. So we are now going to make use of this, and if we make use of this, what it turns out is that this term is going to be nothing but this small y tilde of t is going to be this m omega taken outside as before. Let me box this part out separately. So this m omega taken outside common, this is going to be a cos omega t plus phi. This is going to be a cos omega t plus phi. Of course phi is a function of omega, remember. So I am just omitting this argument in omega for the sake of brevity here, yeah, because otherwise there will be too many braces and brackets and stuff like that. Yeah. Now I want to take 2j common out. Yeah. So what I am going to do with this is I am going to write this term, I can replace this term with minus b upon 2j. Yeah, again I am going to multiply above and below by j. So if I multiply above by j, it becomes j squared upon 2j, and j squared is nothing but minus 1. So I am going to replace this term. So then I push in this minus sign inside, so this becomes a plus and this becomes a minus. So in other words, what we will then have is plus b sine omega t plus phi, or so I believe it should be, unless I am much mistaken, right. Yeah, I suppose that is what it is. If I take the minus sign out common, so it is, yeah, so it is sine omega t plus phi, yeah, absolutely. Okay. So I can say that this is going to be nothing but, notice I am going to just pull out this a squared plus b squared out common, and then take this m omega, and now I am going to just say this is a upon square root a squared plus b squared cos omega t plus phi plus b upon square root a squared plus b squared sin omega t plus phi. Okay. Notice what was the input that I started with? Yeah, what was the input that I gave to this system? If you take this RT here, in other words, this just means this RT is nothing but a squared plus b squared under root, and then this is a upon square root a squared plus b squared cos omega t plus b upon square root a squared plus b squared sin omega t, right. So if I now write this, this is going to be some mi, this is the mi input, so this is mi is basically nothing but the square root of a squared plus b squared, and then this I can write this as some let us say sin theta, and this as some cos theta. So let us say this is sin theta and this is cos theta. Yeah, so basically then I had an input which was mi sin theta cos omega t plus cos theta sin omega t, which is nothing but sin of omega t plus theta. So essentially this input was nothing but this mi times sin of omega t plus theta, and now here what I get back is, if I replace it, I will get back this mi, which is basically the amplitude of the input, times m omega times, again I have the same thing here, right. So this is basically my sin theta, recall that is the way I defined it here, no. I call this sin theta, which was multiplied with cos omega t, now it is just multiplied with cos omega t plus phi. So then this becomes sin of omega t plus theta plus phi. So here I have established what I set out to prove, or what I claimed initially, which is that if you give a sinusoidal signal of amplitude mi, so this is the amplitude of input, yeah, and which had an initial phase, so this was the phase of the input, yeah, then at the output I get another sinusoid of the same frequency, except that the amplitude of output gets scaled by m omega and phase of output gets shifted by phi omega. So this encapsulates the role or the effect that the system has on the input signal. In other words, if you want to understand what a linear time invariant system does to a sinusoidal input of a certain frequency, all that you need to know is the amplitude gain, that is m omega of the system at that particular value of omega at which you are applying the input signal, and the phi, the phase function, right. So this is the magnitude function of the system, and this is the phase function of the system, alright. So if you know what the magnitude function and the phase function's value is at a certain frequency, then you know exactly what will happen to a signal or a sinusoidal signal of that frequency when it is applied to a linear time invariant system. So let me just summarize that important statement here. An LTI system gives an output of the same frequency as that of the sinusoidal input. It only scales the amplitude by m omega and shifts the phase by phi omega, right. So these are the only two things that can happen to an LTI system. Very important. Immediately I can think of a system that is not an LTI, which is something like a saturation block, yeah. So for example, if you have a saturation block like this, and if you apply a sinusoid of, let's say, very big amplitude, if this is your input, which is a sinusoid, yeah, what will happen at the output is, in all likelihood, you will see that the output, it gets clipped. If the amplitude is very large of the input, then in the oscilloscope at the output port, you will see that it has got clipped like this, yeah. So therefore this obviously has frequency components. If you do a Fourier series analysis of this periodic signal, you will see that it has not only the fundamental harmonic, but it has also many other harmonics. So you give an input of just one frequency, but at the output you have several other frequencies appearing, and that is simply because this saturation block does not qualify as a linear time invariant system, which is essentially why we were so interested in understanding these beautiful properties of linearity and time invariance right at the beginning of our course, alright. So remember that. The other important thing is, of course, as is obvious from this saturation block, the output is independent of the input amplitude. What I mean by that is, if you have an input amplitude of 10 at a particular frequency, it will be scaled by a factor 5, so you will have an output amplitude of 50. If you have an input amplitude of 100 at that same frequency, then you will have an output amplitude of 500. Yeah, so it will be scaled by the same factor, whether the input amplitude is 50 or 5 or 5000 or 5 billion. On the other hand, if the system is not an LTI system, then it will also depend, it might also depend on the amplitude of the input signal, okay. So these are all beautiful properties of the linear time invariance that we are trying to now harness here to our benefit. Before we close this module, let me just give you a brief introduction into some other aspect of this frequency response. So it then turns out that if you want to identify what a system does to several sinusoidal inputs, the experiment for that is if you have this system which is a black box. We will talk more about this once we have covered Bode plot and seen how different system blocks can be treated, yeah. But the idea is that if you want to run an experiment such as this in order to find out, so here you have at the input some sinusoid, yeah, and let us say you can vary the frequency of the sinusoid, okay. So you apply sinusoids of varying frequency at the input and you observe the output, okay. So at every omega, the idea is at every omega, note the ratio of output to input amplitude, yeah, and that will give you, that gives m omega. By the same token, so I am not writing it down here, by the same token if you look at how much phase shift had happened. So for example, you have this reference frame, you give a sinusoidal input of particular frequency and you look at the output and see how much phase shift has occurred. That will give you your phi of omega. So you carry out this experiment by applying sinusoids of different frequencies at the input terminal, look at the output and see the ratio of the output amplitude to the input amplitude, that will give you m omega, and the phase shift, and that will give you phi omega, and then you just sketch that, okay. So on the same graph paper you have m omega and then you have phi omega, so you can sketch this function, yeah. And it will turn out that once we have done Bode plots in some detail, you will see that this plot will actually be useful in something called system identification. Let me write that down in a different ink. So this sort of an experiment helps us in system identification, okay. So of course, as I said, this frequency domain methods give us a parallel way into designing or synthesizing controllers like we have seen with root locus, but we will not focus on that in this course, but I will at least try to give you some flavor of how this sort of a method, this frequency domain method, is useful in another application which is system identification. Suppose you have been given a black box, how do you obtain its transfer function? Given that you know it is a linear time invariant system, all you do is over your frequency range of interest, apply different sinusoids, look at the scaling of the amplitude, look at the phase shift, plot them, and from these, of course later on when we are done with Bode plots, you will see that from these m omega and phi omega plots we can approximate the locations of the poles and zeros of this particular system, okay, but all in good time. So for this lecture up until now, thank you very much.